All right, so now we're going to prove that if we have a situation where we've got multiple classes and it is separable, meaning that there exists some set of vectors in a matrix here where it has a norm of 1, basically, that correctly classifies everything, then doing these perceptron updates, like we just talked about in the introduction, will in fact correctly, after a limited number of updates, so of mistakes and then updates, it will correctly classify all future points in the training set. There's a limited number of mistakes. The result is fairly similar to the result for the perceptron. So I'm going to come back to the details of this and just review the proof for the regular perceptron with 2 classes. And then we'll just see how we can extend what we do for the regular perceptron to the multi-class perceptron here. So the idea behind the proof for the regular perceptron is if it is separable by a margin of gamma, which then will make fewer than r squared over gamma over y squared, gamma squared mistakes. So separable with this margin means really that there's some vector b star where b star has length 1, right? So it's actually measuring distance, where if you take any point and you dot it with b star, then if it's blue here, it'll be greater than gamma. If it's purple, you dot it with b star, it'll be less than negative gamma, right? Put a negative there to emphasize that. And so that's how we can say it separates with a margin gamma. And then we've got another distance, which is the distance of all the points from the origin. That's going to be less than r. Because obviously if we had a point way out here, still separated by gamma, but an update involving that point could really screw up your vector. So in order for our vectors not to be screwed up too much, there has to be some limited norm for each of the vectors. Right. And so the basic idea behind this proof is that each time we do an update, so let's say I want to play out a movie here. I'll just do this in yellow actually. So say that initially we've got no vector, and then we pick our first point, and so we do an update. Now we've got a vector like that. This is a horrible color. Sure. Okay. So initially we've got this vector. Now let's say that we look at this point. The dot product with this is negative, so we predict this to be of the purple class, which is incorrect. And so therefore we're going to take this vector and we're going to add it onto that vector, right? So we're going to get something like that. Now, why did we get this one wrong? Well, because this angle is greater than 90 degrees. Or in other words, the dot product between this and this is negative. And so therefore, when we take this and add this one on, the length of our vector will increase by less than this. Right? So the resulting vector will be less than the length. Sorry. Since the angle here is greater than 90 degrees, I know this is less than r. I know this is less than r. So this new vector will have length less than r squared plus r squared. That would be Pythagoras. But it'll be less than that because the angle is greater than 90 degrees. So this would be root 2 times r, right? And so in general, whenever we make a mistake, here it looks like we got the perfect vector by chance after 2 steps. But whenever we make a mistake, that means that the angle was so big that, well, the length overall of our vector is increasing like this. So after After 5 mistakes, what's the max length? The length of our vector will be less than root 5 times r. Okay, so that's just looking at the overall length of our vector. On the other hand, each time we make an update, whether it's from this point and then this point, the component in that direction increases by at least gamma each time, right? So we could say, let's call this the y direction. So v in the y direction is going to be greater than, after 5 mistakes, it would be 5 times gamma. And so you can see that this is increasing at a linear rate with the number of mistakes, whereas this is increasing as the square root. So obviously r is going to be bigger than gamma, but over time this will overtake that, and obviously the length in the y component can't be bigger than the overall length of your vector. And so this means the thing that has to happen is that the algorithm stops, that there's convergence. So that's smaller. Okay, so after m mistakes, we know that the length of v is going to be less than root m times r, and we know that vy is going to be greater than gamma m, and obviously this has to be less than that. So we know this is less than this is less than this has to be less, yeah. Right. Good. So this would have to be less than that. Therefore, m gamma has to be less than root m r. Cool. And so we're going to solve for this. We can square both sides, and we're going to get m is less than r squared over gamma squared. Okay, so that was the proof for the regular perceptron. And so to review, the idea is that over time we can see that this component in the, we can think of this as the component in the v star direction keeps getting bigger and bigger, right? And overall, the rate at which it grows, well, it's got this square root, so it doesn't grow that quickly, which is why it has to stop. And so we're going to see that we can apply this same idea for the multi-class perceptron. That out of the way. All right, so first of all, I want to go a bit through the notation. So training set, okay, so here, instead of a vector v star, we're assuming that there's a matrix m star of unit vector norm. So first of all, I want to talk about what these matrices are. So really, we're going to have 3 vectors, right? Call this v1, v2, and v3. And in the notation they used in the paper, they could have written this another way, but they just put these into a matrix, which they called M. So v1, v2, v3. They put these as the rows. And they called this equal to M, or there's M and there's M star. M star is like our V star. It's got, norm 1. And it's in the directions that do separate it perfectly. And, okay, So we've got a matrix. What do they mean by the norm of m star equals 1? The norm of m star equals 1, that's equivalent to just the norm of each of the vectors added together. We'll put vi, and then we'll just sum over I. But that's equal to 1. We're running out of space here. All right. So, right. So sum of a bunch of vectors equals 1, so that's similar to having length 1. So what does this margin become? So the margin really, so this is when we take the dot product with the correct one, and this is when we take the dot product, well, with the maximum of the other, so the next highest. If that difference is greater than, all right, so the minimum of that, which that'll be the margin. So this means no matter what point you pick, always the correct one, so this one dotted with that, minus the next best one, which would probably be V2 in this case, this one dotted with that. The difference between them is always at least gamma. That's why gamma is our margin. Okay, so then the number of mistakes is at most this, and this happens to be a generalization of this. It's exactly the same when there's only two classes using two vectors. So let's see how this works. The idea is going to be analogous to what we did for the regular perceptron. So what we're going to do is, instead of just looking at, all right, so there's two parts. There's the overall length of the vector, and then there's the length of the vector in the correct direction. And now it'll be the correct directions because there's 3. So we need to basically bound both of those. So let's first do the length of the vector, the length of our matrix overall. So what we're going to do is we're going to start with some matrix, right, a bunch of vectors, and then we're going to try to figure out how to write this out well. So let's say that I'll call this V1 star, V3 star, V2 star. Now let's, there, no. Okay, so let's say that we've got, we've got something like this, and like that, and then we pick a new point, and this one wins, when this one should have won. Well, we're going to say, okay, we're going to update this one, so that will become longer by that. That'll become our new V1. And this one, we're going to subtract that off. So we're going to get something like that. All right. Cool. So, now the reason this one won was it had a greater component in that direction, right? And this one did. And so when we add this component onto here, it's going to increase the length of V1 by less. Now let me think of this. Right. So if we think of the parallel parts, the parallel part here will be increased by less than this one is decreased by. Is that correct? Okay. I want to draw a picture here. So we've got some point, right? And then we've got the correct vector, v1, say. And then we've also got the vector that beats it, v2, which isn't the correct vector. And each of these have components in the direction and component perpendicular. So this one, we're going to increase it by that amount. Whereas this one, we're going to decrease it I can see that we decrease it to 0, and then the component parallel starts to increase again. Alright, I'm actually having trouble figuring that out, so I'm just going to jump into the equations and the math. So in this case, v2 vector dotted the point that was misclassified was greater than v1 vector dot that point, which is why we're doing our update. And so then v2 goes to v2 minus the point, and v1 goes to v1 plus the point. Alright, and so I'm going to put primes here to show that these are the updated versions. And so v2 prime, and we'll take the norm squared of each of those, plus v1 prime squared. This will be equal to, well, we'll get v2 squared plus v1 squared, right? And then we'll get plus 2p squared, right, from this dotted with itself. And then we'll get the cross terms. So we'll get minus 2 v2p plus 2 v1 dot p. And okay, so remember v2 dot p was bigger than v1 dot p. So therefore, this part is going to be negative, which means overall this is going to be less than or equal to v2 squared plus v1 squared plus 2p squared. So therefore, each time, so here I only looked at these two components because v3 wasn't changing, but overall this norm of our matrix is increasing by less than 2p squared each time. So therefore, the norm of our matrix, now it's not m star, now it's the actual matrix, as we run our perceptron, will be less than or equal to 2 times the number of updates, p squared. I'll put a square in there. Alright. Right, this makes more sense to me now. Unfortunately, I don't have a better explanation rather than this. My intuitive explanation is really just the same thing as this algebra. So let's give ourselves a bit more space. Alright, so this was for, we bounded that, right? The norm of the matrix. Next of all, we want to do what's analogous to this. Here, Vy, so this was the component really in the direction of our V star that separated them, right? So now we're going to want our components in the direction of M star. So we're going to do M dotted with M star, which we're going to define to mean the same thing as, we can take sum over I of Vi vector dotted with Vi star vector. So we have our perceptron that we're updating, and we're dotting the V1 component of that with V1 star. Cool. So we're going to do that now. And M dot M star. Okay, so that's just a bunch of dot products. And again, let's say that we're updating V1 and V2, because we predicted V2 and we should have predicted V1. And so this was a point P1. Okay, so again, we're going to have the same updates here. Now let's look what happens to M dot M star. So M prime dot M star okay, I just want to look at the difference. So really, I want to look at V2 prime dotted with V2 star plus V1 prime dotted with V1 star. This is going to be equal to so we get V2 dot V2 star. This is just the old part plus V1 dot V1 star plus the new plus what's different, which is we've got for V2, I guess it would be minus. So we decrease that minus P dot V2 V2 star, right? Plus P dot V1 star. Cool. And we know that since this M star always classifies correctly, obviously V1 will be, P will be more in the direction of V1 than V2, and so this is bigger than that, and so therefore overall, oh, this is bigger than that by a margin, right? It's bigger than that by the margin gamma. So this is going to be greater than or equal to the original amount plus gamma. Yeah. Cool. So therefore M dot M star, each time we can see that M dot M star is going to increase by gamma, right? So this will be greater than M gamma, number of updates times gamma. Great. Now, somehow I want to figure out something related to the norm of m from this. I know this is analogous to this, right? Just Vy, except now it's for a bunch of vectors. So what we can do is m star is just these, right? And when we do the dot product between them, what we really mean is the dot product of each of those. And so we can think of putting these together in just in a big row, and we can think of m star as being v1, v2, so it would have lots of components, right? Just string it together into one big vector. And so then m star is really just one really long vector with norm 1, and we've got some other vector dotted with x greater than this. Since this has norm 1, then obviously the norm of this, the norm of m, has to be greater than or equal to m gamma. So by looking similarly, we could, those should be stars. Similarly, we could, for m without the star, we could write something similar. Okay, so then it just reduces to the same thing as before. Excuse me. Except now we've got an extra 2 in here because we're always updating 2 vectors at a time. And so this will have to be less than that. So m will be less than 2. Well, this is really the norm of p, which would be less than r squared, right? So 2r squared over gamma squared. Cool. So I like that idea. Basically, you can look at this in higher dimension as just big vector, which is kind of interesting. And our prediction is based on this part dot this part versus that part dot that part. So, okay. And so what I assumed here is I assumed that we just took the correct vector and the maximum other vector that was wrong, that needed, and just updated those two. You can update anything in the error set, but then basically you're just splitting it into a bunch of smaller updates. And so what we're doing here will, I believe, still work. Yeah, I'm pretty sure it'll still work. Haven't thought it through in detail. All right.